Welcome to Let's Get to the Marks, going over a A-level chemistry question on the enthalpy of solution. It's got a practical involved as well. So let's get into this. Question 1. Anhydrous magnesium chloride can absorb water to form the hydrated salt magnesium chloride 4H2O. Suggest one reason why the enthalpy change for this reaction cannot be determined directly by calorimetry. Pause the video, have a go, then unpause and watch the answer. Okay, the issue here is that you're looking for an energy change, and when you add the magnesium chloride to the water to form hydrated magnesium chloride, some of the MgCl2 is actually going to dissolve in the water and not react to form hydrated magnesium chloride. And so your issue there is that you've got an energy change involved with dissolving the MgCl2. So you've got the enthalpy of solution happening as well. So you've got some energy being released from dissolving that. So how can you tell what energy is involved in hydrating the magnesium chloride? You can't, it's inaccurate. Therefore, the best way to calculate the enthalpy of hydration for magnesium chloride is via calculation, and that's what we've got here in 1.2. Some enthalpies of solution are shown in table 1. So we've got the enthalpy of solution here. Calculate the enthalpy change for the absorption of water by magnesium chloride to form hydrated magnesium chloride, and use the data from the table. So we want to set out an equation just like it's telling us to up here. So MgCl2, which is magnesium chloride solid, plus 4 molecules of water makes MgCl2.4H2O, which is the formula for hydrated magnesium chloride. So now that we've done that, we want to draw an arrow going down because we've been given the enthalpy of solution, which is the energy released when you ionize basically a molecule into solution. So we've got 2 plus ions and 2 chloride ions, and we've got that coming down on both sides. And this is how I like to do it. There are other ways to do this. And then I write minus 155 there for the enthalpy of solution for MgCl2 and minus 39 for MgCl2.4H2O. Then I draw a big fat green arrow. It doesn't matter what color you use. I use a nice like bright color so it shows up, going round from left to right. And I draw my arrows on it. Now, if the arrows match, I keep the symbol the same. So the arrow from my green arrow going round matches the black arrow, so I keep it at minus 155. However, with minus 39, I've got one arrow going down for enthalpy of solution and my green arrow going up. So I reverse the symbol when I do minus 155 plus 39 equals minus 116 kj per mole to the minus 1. And here we go. So that's how I work that out. Okay. Describe how you carry out an experiment to determine the enthalpy of solution of anhydrous magnesium chloride. You should use about 0.8 grams of anhydrous magnesium chloride. Explain how your results could be used to calculate the enthalpy of solution. So we've got a big fat 6 marker here. What I'd start with is you want to measure out 50 centimeters cubed of water. Use a measuring cylinder or a pipette, so give a sensible suggestion for something to measure that out. You could use 100 centimeter cubed. It doesn't really matter. Just don't say like 1 centimeter cube of water, which isn't going to dissolve the amount of magnesium chloride we've got. Now pour that into a polystyrene cup with a lid, because what that's going to do, it's an insulator, it's going to reduce heat loss, and we're going to get a better reading of temperature change. Therefore, it's more accurate. Take some initial measurements of the temperature and plot these on your graph, but you're going to do that later. So just take some initial measurements. Now, your initial readings of temperature, you must take at least 2 readings so you can see that it's constant. You want to take maybe 2 or 3 and make sure that they're constant, the temperature not fluctuating. Now, then you want to use a before and after method to weigh out the 0.8 grams of anhydrous magnesium chloride. Okay, what do we mean by the before and after method? Well, if you've weighed it out into a crucible and then you tip that into the solution, you need to weigh the crucible after so that you can subtract the weight after from the weight before and work out how much you've actually added. Now record, because if it's not quite 0.8, we need to adjust that for our calculations of moles later on. So add the solid now to the water, record the temperature every 30 seconds for 5 minutes. The temperature is going to go up as energy is released. Plot a temperature versus time graph with your results and look for a clear trend. So you should see a clear trend on the graph. And this is what your temperature time graph is going to look like. You're going to have temperature on the side, and time at the bottom. Here's my initial recordings, which are going to be constant. And then you can see here, got a bit of a trend going on. It's going up and then going down. So I've got a clear trend right here. It's increasing, then decreasing. So that's my clear trend. What we want to do now is extrapolate the line. So you stop when there's a clear trend and then extrapolate by drawing a line through the trend back to intersect the point of addition of the solid. So where did we add the solid? We added the solid after the second reading there, the second cross, which was the initial temperature. So we added the solid there. So I want to draw a line back from my trend like this, and then that's going to intersect the line where we actually added the solid. And that here is IT, my initial temperature, and the highest point on my temperature recordings is the final temperature. So that is delta T, the difference between FT minus IT, and then we've got our change in temperature. Okay, now I can just use Q equals MC delta T to work out Q, right? I just do the mass 0.8 times specific heat capacity of water times delta T, and I get Q. Now Q is in joules, but our answer needs to be kilojoule per mole because it's enthalpy. So we're going to divide by 1,000 to put into kilojoules, and then I need to get it per mole, so I need to divide by n, the number of moles. How are we going to work out the number of moles? We need to explain this to show we understand. We're going to take mass, which is 0.8, and divide it by 95.3, which is the MR of MgCl2. You can see I'm working it out up here. However, listen, you do the weighing before and after method in this. You may not actually, you might have 0.798 grams actually added, even though you tried to add 0.8. That's fine, because when you calculate moles, it will adjust for that, and your answer will be in kilojoules per mole. And there we go. That's how to do this method and get your 6 marks, which is nice. So you just need to know this one, and you need to know about that extrapolation of the lines, and the point where they intersect is where the solid was added. Okay, for this next question, it's a graph plotting question, and what we've got to do is we've got to use table 2 to plot a graph of of delta G over TK. So yeah, and use that to find delta S, use the gradient. So it's really a 5 marker, and you get about 3-4 marks for the graph. So all you've got to do is plot the points on. So go 298 at 298. What's the temperature? So at 298, it's minus 592.5 kilojoule per mole. That's the free energy, delta G. And we just got to plot these points on, which is very hard to see on this. So I'm just going to show you how to do it, but bear with. Like it's very difficult to put this all on the screen and show you how to do all of this. I got that point wrong. So they do give you plus or minus 1 baby little small square when you're plotting the points. So this is minus 594.2, should be there. And then I want to go to my next point, which is 260. That's quite easy because that's on the line. And then zing up to minus 598.8. And then for the final one, we're at 240, which is right at the start of the x-axis. And we can go up to minus 602, and then draw a line of best fit. It should go through all the points on this one, your line of best fit, no curves, no kinks. So if you get all the points correct and you get your line of best fit correct, that means that you will have scored, and your plots and your line of best fit, you'll get 2 marks. Now we need to work out the gradient. So if you can calculate x, we want to do what we want to do. We want to work out x and we want to work out y. You can pick any 2 points on the graph to do this, and then do y divided by x, and you'll get the gradient, and then convert the gradient units from kilojoule per mole into joules, which is for delta S, because delta G is in kilojoule per mole, delta S is in joules per mole. Joules to the minus 1, K to the minus 1, mole to the minus 1. So what we're going to do here, I'm going to do my graph up here. I'm going to find a point where my line of best fit hits a nice easy bit to read. So there it's at 295, and I'm going to come across to here and zing down to the line where it's nice and neat, and I can work out these fairly simply. So, and I've got 597.2, and that's minus 593. So I want to put in minus 597.2 minus 593, and I get 4.2. Whether it's minus 4.2 or just 4.2 doesn't matter. So because we're looking at the difference in y over the difference in x. So 4.2 divided by 25, and I get 0.168. Now what I need to do is, that is in kilo, that's going to be kj, and I will need to turn that into joules. So I'm going to times by 1,000, and going to get 168. And I think they accept anywhere between 0.167 and 0.170. Or sorry, 167 and 170. Yeah, 167 and 170 once you've times by 1,000. So I got 0.168 from my units. And again, yeah, there we go. That's how you do the graph and convert to delta S. So delta S is in joules. So times 1,000, bish bash bosh, and we get 168.
You're still here? It's over.